Okay, guys, let's get started. Today's lesson is on language transformation. Uh, so let's just dive right in because we don't have any time to mess around. Okay, let L be an arbitrary language over the alphabet 0, 1. Prove that the following languages are also regular. You probably won't get to all of these. This is the most true sentence I've ever read in my life. Okay, flip odds L takes flip odds L is the function flip odds of W, where W belongs to L, where the function flip odds inverts every odd indexed bit in W. So let's look at an example. Flip odds of, let's apply this function to the string 0, 1, 1, 0, 1. Right, so, no, so we're going to start zero indexing, just because I decided, because you answered, no, okay. So these are the odd bits, right? The index 0, index 1, index 2, index 3, index 4. Index 1 and 3 are odd, so we will simply flip them to be even. Sorry, we'll flip them to be their complements. So it'll be 0. This becomes a 0. The 1 stays the same. This becomes a 1. And this remains a 1. So far, all we've done is we understood the function flip odds just flips the odd index bits of the string. So what else does this question tell us? It tells us that L over here is an arbitrary regular language. So if L is a regular language and W belongs to L, W is every string in the language L. W is a particular string in the language L, my bad, sorry. So if we enumerate all of the possible strings in the regular language L, we just list them all out. Let's say there's 1,000,000 strings in the language L. And we flip all of the odd bits of each of the strings in the language L. We end up with flip odds L. Flip odds is just a function applied to a string that flips the odd bits. Okay, so if L is a regular language, this implies that there is a DFA that accepts the language L. So we can start there. L is regular. This means, I can't spell, whatever. There is a DFA that accepts the language L. Okay, well now the question is asking us to prove that this language flip odds L is also regular. So we want to prove flip odds, which is a function applied to all of the strings in the language L, is regular. So how do we do that? What are the ways to show that a language is regular? One way that we learned was we can build regular expressions. Another way that we learned is we can construct DFAs. Another thing that you guys hopefully learned in lecture was NFAs, right? So the language is accepted by regular expressions, the language is accepted by DFAs, the language is accepted by NFAs are all one and the same. They are all regular languages. So we want, in order to prove that flip odds is regular, we will build an NFA that accepts flip odds. So let's think about this intuitively. We have a desk. We have a desk right here. There is a black box on the desk, which is a DFA for the regular language L that is on this side of the equation. So we'll call this machine M. There is a light bulb on this black box that if I feed in characters into this machine M, which is a DFA for M, and the string is accepted by the regular language, this light bulb goes boop and it lights up. So this is my DFA for M. I have access to this as a black box. What is the 5 tuple that represents the DFA? So this is my machine M, okay? This accepts the language L. I need to prove that flip odds L is also regular, which means I need to build an NFA that accepts flip odds using this DFA as a black box. So what I'm getting in as input is some string. What I'm receiving as input is some string which has had all of its odd bits already flipped. So I'm standing here. This is me. And I have a string. I had a string. And what I need to do is I can only consume my string once, and I can only consume each character once, and I can only consume from left to right. So I need to pick a character from the string. So I pull a character out of the string. If it's even, I feed it into the black box over here directly. If it's odd, I flip the bit, and then I feed it into the machine. Does everyone see what's going on here? Does this make sense? Stop me if you have questions. So just to reiterate, I'm consuming a string, flip odds of W, that has all of its odd index bits flipped. I have a black box on the desk that accepts the regular language L. I'm reading flip odds of W, some string. If the character is even, I'm grabbing it from the string and throwing it into the machine. If the character is odd indexed, I flip the bit and then throw it into the machine. So this whole process is my new NFA, M prime. So M prime is a 5-tuple that has an alphabet, a set of states, a start state, an accept state, and a transition function. I'm going to put primes on all of these to distinguish between the transition functions of my DFA M and all of the tuples, elements of the tuple for M, and all of the tuples, elements in my tuple for M prime. So let's build this NFA that accepts flip odds. Okay, my alphabet's going to be the same. Let's think about my states. When this red guy is standing over here, he needs to keep track. He can't count. The reason he can't have a counter is because a DFA or an NFA has to have a finite number of states. If we're counting, we can get to an infinitely large number of states. This guy needs to keep track of, hey, is this character that I'm pulling an even index or an odd index? Is this even or odd? So not only do I need to keep track of the state of my black box, which is Q, I also need to keep track of whether or not the bit that I am currently passing into the box is even or odd. So the states are going to be Q cross some sort of flag indicator variable to keep track of even and odd bits. So the first bit that I pass into my machine, this DFA starts in its own start state, S, right? It has its own start state. The first bit that I pass in, if I'm zero indexing, is that going to be even or odd?
Zero index will be
right. 0 divided by 2 is 0. So I go to the machine, I grab its start state, and I say that the state of my new NFA M prime is S comma even. And just for extra clarity, the states of my NFA M prime are tuples of Q comma a flag, which is even or odd, where this Q denotes the state of the black box DFA, and this denotes even or odd bits being passed in. Okay, so I have this NFA. I'm building this NFA right now. How do I know when I've reached an accepting state? I know I've reached an accepting state when two conditions are met. If, for whatever reason, this black box ends up in an accepting state. But I have not consumed all of the characters. It doesn't matter. That's not what an NFA is. An NFA leads to an accepting state when, one, you have consumed every single character in the input, and two, this black box on the desk has its bulb glowing. So when would I be in an accepting state here? When do you think I'd be in an accepting state? If this light bulb lights up, right, that means the string belongs to the language M. And if I've consumed every character of the input, those are the two conditions that need to be met in order for my NFA to accept this string. So I take the accepting states of the DFA that I have, this black box over here, and I take a cross product with even and odd. It does not matter if my string has an even length or an odd length. As long as I've consumed every single input character, regardless of whether or not this is even or odd, if this black box lights up, I know the string belongs to the language M. Now the transition function. So just a reminder of what the transition function does. Jeez. So the transition function, very simply put, is we have an old state. Again, this is the transition function for the NFA. It's delta prime, not the DFA. We have our old state. We have our input character. And this leads us to a set of new states. Okay, we have our old state. We read one character from the string over here. We read one character from this string, and we end up in a new state as a result of our transition function. But wait a minute. The states of my NFA over here are all tuples. They're q comma some flag. So if I say that my old state is q comma even, and I receive some input character, let's call it character C. So I'm in the state q comma even. I've received an input character q comma C. What did I say I do with even bits? Do I throw the even bits into the machine or do I flip them? What's up? Did someone answer or no? I just pass it on, correct. If it's even indexed, I just grab it and pass it on to the machine. So if I'm in state Q and I say, hey, this is an even bit that I'm reading, I just pass it on into my machine. What is the transition function for this black box DFA? Right. This is the transition function, delta. So for this DFA, the states are just Q. The states for this DFA are not tuples. So if I wanted to transition the DFA into a new state, from state Q, I would simply do delta of Q comma C. Everyone sees that, right? If I consume input character C, I have this DFA, I go delta of Q comma C. That brings the DFA into a new state. So let's zoom out back to what we were doing. We have this transition function delta prime. Our old state is Q comma even. I've consumed an input character C. Now, as he just said, all we have to do is pass this character on that I've just consumed from here into the black box if it's even. Well, we just said that you do that by calling delta of Q comma C. Okay, if the last bit I passed in was even, will the next bit be even or odd? Odd. So I switch my internal flag variable from even to odd. And I'm going to put the delta prime transition symbol around this. And since I said I was building an NFA, we have a set of states, not just one state. Okay, now suppose the man standing over here has grabbed an odd bit. So the DFA black box is in state Q. The man standing on the side of the machine has grabbed an odd bit, and he's grabbed input character C. Remember, if he grabs an odd bit, he's grabbed index 1. He needs to flip the bit before passing it into the machine. So if my character was 0, I'd pass in a 1. If my character was 1, I'd pass in a 0. We could also simply represent this as C complement. So again, my DFA black box is in state Q. I'm passing in the flipped bit that I've just read. I've taken the bit from the string, I flipped it, and now I'm passing it into my black box. And I'm transitioning from an odd state to an even state because the next character that I will read is even. And that's it. I'm done. So this is a somewhat complicated process. All we are doing is saying we have this function flip odds. W is a regular language. We have a black box that accepts the language L. We have a function applied to every single string in the language of L. We need to prove that when we apply this function to every single string in the language resulting from that is also regular. How do we do that? We take the function that we have applied to the strings, we undo the function, pass it into the black box, and if the black box accepts it, then we're good. If it rejects it, then it's not part of the language. What we've done is we've built an NFA using this DFA as a black box. I'm going to stop here and pause for questions. Does anyone have any questions? And if someone is completely lost, that's okay. This is a tough concept. Go ahead. I'm sorry? No, so here's good point. So do I need a flag for when the input stops? So my states are of the NFA are Q comma flag, right? So let's say I consume my entire input character. I don't flip, I flip. I don't flip, I flip. I don't flip, right? I get to the end. The light lights up. Does it matter if the last one was even or odd? It doesn't matter. As long as I've consumed the entire input string and this light bulb is glowing, I'm good. So that's why the accepting state is the accepting states of my old DFA crossed with the flag even comma odd. Good question. Anybody else? Yeah, go ahead. Oh, why are we doing language transformation? So the question says, prove that the following languages are regular. I want to prove that flip odds is regular, right? You asked the question, right? Okay. I want to prove this language is regular. I'm told in the question, L is an arbitrary regular language. So I know that this language is regular. If I want to prove that this language is regular, if I can transform flip odds into this language using an NFA, then that means that flip odds is also regular. Does that answer your question? Okay. Anyone else? Go ahead.
Could you show us what delta looks like for M, not M prime?
So yeah, what does delta look like for M, right? That's a good question. And the answer it is none of your business what delta looks like for M. We don't know what this regular language is. We know it's a regular language, therefore we know that it can be represented by a DFA or an NFA. It does not matter what the delta for M looks like. It is none of our business what delta looks like for M. All we know is this is a regular language, therefore it can be represented by some abstract DFA as a 5 tuple. Anybody else? Good questions, yeah.
I want to know when to use a DFA versus
Great question. For my language transformation, right? So, what did we say? We said that, so just to reiterate the question, the machine that I'm building how do I know if I should build an NFA or a DFA? That's question one. And question number two that kind of piggybacks off of this is this thing on the right side that I'm assuming is regular, right? Should I assume I have an NFA for that or a DFA for that? Which one are you asking? Are you asking if I should build an NFA or a DFA? Okay, cool. What do we say? So there's a theorem that you guys all studied. The regular languages are equivalent to the language accepted by regular expressions, which are equivalent to the language accepted by DFAs, which are equivalent to the language accepted by NFAs. So why should I make my life hard? If I know this is regular, just build a DFA. Because there's a finite set of state transitions. I do not need to worry about epsilon transitions and all that other junk. I don't need to worry about, in an NFA, right? When I apply a transition function, I can end up in two possibly different states. Why would I want to worry about that? Always assume that this is a DFA when you see a question like this on the midterm. When you see a question like this, always assume that this is a DFA and always construct an NFA because it gives you the most amount of leeway. So let's look at this question in particular. I built an NFA, right? For this question. Do you notice anything about all the states that I built and the transition functions? I'm always only leading into one state, right? Over here, I lead to one state, I lead to one state, right? So I could have easily just built a DFA. How? Done. Right? I just erased the set notation and now I have a DFA. So I would recommend in the question, assume that this thing on the right you have a DFA for, and you are building an NFA. Any more questions? These are good questions.
Stupid one. So this one just for alphabet 0 and 1. What if we have extended alphabet?
Yeah, so what if we have an extended alphabet? I don't think the complement, it says flip odd bits, right? So the question is, what if we have an extended alphabet? What is the complement of 2?
1 not 0.
Huh?
0 and 1.
Sure. So the thing is, that's 2 characters long, right? You need, what is it? You can represent the numbers 0 and 1 with 1 bit. Representing 2 needs 2 bits, right?
Yes.
So I can only consume 1 input character at a time. So there's a reason this question was written this way. It'll be interesting. Well, another thing you could do is just literally use the number 2, right? So you could use the number 2 and put it as part of your alphabet right here. But then how do you invert 2? I don't know. Maybe you can look at like the 2's complement equivalent and then switch it and make it positive and do some modulo. I don't know. I don't think this question would scale well to more than binary inputs. Any other questions? At a high level, is this making sense? Give me a thumbs up or a thumbs down. Okay, I'm seeing some thumbs up. I'm seeing some of these. I'm seeing very few thumbs down, which means I'm kind of doing my job. Let's move on to the question that's on your homework. This is tough, so I'm going to go slow. So, the language is cycle L. We have